Hey, what's up everyone? Today we are going to be looking at series in section 11.2. So this video is just about introducing to you what a series is and the notation behind it. All right. So a series is simply defined to be the sum of the terms in a sequence. So we take the sequences that we worked with in the first section, and all we are doing now is we are adding those terms together, the sum of which is known as a series. We're going to primarily be working with partial sums. The nth partial sum of a series is nothing more than the sum of a finite number of consecutive terms beginning with the first term. And notation matters here. We will represent our sum with a capital letter S. So when you see S sub n, that represents your partial sum. S sub 1 for the sequence that's listed up at the top would simply be 3. You're just going to give the first term of the sequence because there's nothing else to add with it. But then if I want S sub 2, that notation means add the first two terms of the sequence together. So 3 plus 7, of course, gives me the sum of 10. S sub 3, add the first three terms together. 3 plus 7 plus 11 is 21. And I think you get the idea from there. All right, example 1. If A sub n has the terms 2, 5, 9, 14, 20, find S sub 4. Notice that's a capital letter S. So that wants us to add the first four terms of the sequence together. 2 plus 5 plus 9 plus 14 there. That's going to give us 30. All right, in the next sequence, you are given it explicitly as a formula. We want to find S sub 3, so that means we're going to have to first find the three terms of that sequence. All right, so A sub 1, if I plug 1 in for n, 2 times 1 squared minus 1 will simplify to 1. A sub 2, 2 times 2 squared minus 4, that will simplify to 7. A sub 3, 2 times 3 squared subtracted by 1, that'll simplify to 17. So now I find S sub 3 by adding those three numbers together, and I end up with a partial sum of 25. All right, now there's an alternate notation that we can use to represent a series. It's called summation notation, or it's often referred to as sigma notation. We use the Greek capital letter sigma, which it looks like kind of like an E. And anytime you see that symbol mathematically, it's going to represent a sum. Just think add, all right? Now there's going to be three parts to this notation. Underneath the sigma, in red, you have a variable k, known as the index of summation, and that is set equal to a number, in this case 1, known as the lower limit of summation. All that does is tell you what's the first number that you're going to plug in for k in the explicit formula, which is represented in blue, 2k. Then we also have above the sigma, we have another number 5 in this case, that's known as the upper limit of summation. And that simply tells you what's the last number to plug in for k before you add your values together, okay? So if we look down below, I have this one worked out. We would read this as the sum from 1 to 5 of 2k is simply 2 added with 4, added with 6, added with 8, added with 10, which results in 30. So notice we plug the numbers 1 through 5 in for k. We got our 5 results there and simply added those together. All right, in example 2, we want to find the sum from 1 to 4 of k squared. So I'm going to plug 1 in first for k. 1 squared is 1. I'm going to add that to 2 squared, or 4. add that with 3 squared, or 9, add that with 4 squared, or 16. And I would stop there, given that the upper limit is 4. So 1 added with 4, added with 9, added with 16, results in 30 again. Now that sum there, that is known as a finite series, because we had a finite number of terms being added together. The second series here, this is going to be an infinite series in that we don't have a set value for n, the upper limit, okay? So all we're going to be able to do is kind of expand this sum out. We won't actually be able to find the overall value. So the first number I'm going to plug in for k is that lower limit of 2. 2 times 2 plus 1 is, of course, 5. Then I'll plug in a 3 for k. 2 times 3 plus 1 is 7. Add those together. Plug in a 4 for k. 2 times 4 plus 1 is 9. I think you get the idea. This pattern's just going to keep continuing. And it's going to continue all the way until I get to the upper limit of n. Now, if I plug that in for k, that's going to result in a final element of the sequence 2n plus 1. All right, lastly, express the sum 2 plus 6 plus 10 plus 14 plus 18 using summation notation. So ignore the plus signs right now, just focus on the numbers. To go from 2 to 6, 6 to 10, 10 to 14, and so forth, you're just repeatedly adding 4. So we need to come up with an explicit formula for those terms. I would begin it with a 4n then, right? Repeated addition is the same as multiplication by 4 in this case. And then I'm going to have to subtract off a 2 there, right? Because if I plug 1 in for n, 4 times 1 is, of course, 4. But I need the first value to result in 2. So that's why I've subtracted a 2 off. All right, so now we can bring the plus signs back into play and create a sum here, or a series with the summation notation. I would make my formula 4k minus 2. The lower limit, I'll just set at k equals 1, with the upper limit at 5. Why 5? Because the last term that's being added here is the 5th term, and I would find that by plugging a 5 in for k. All right, now I want you to pause the video, work through the problems in practice 1, and then come back to the video, check your work with mine to make sure you're on the right track.